let's continue this last module as part of this advanced reinforced concrete design. We are discussing analysis and design of two-way slabs. In this module, part of the module, we are going to discuss, I think previously we discussed about what are the types of slabs, difference between one-way and two-way, and the code coefficient method. In this module, we are going to discuss about direct design method. There are two popular methods that are available for the design of two-way slabs, which we have discussed in the last part of the module. One is the major one is the direct design method, and a more generic one is the equivalent frame method. In this module 10.2, we are going to discuss about direct design method. Okay. So what are the expected learning outcomes? After the student has gone through this video, he or she should be able to explain the limitations of the code coefficient method, why code coefficient method cannot be applied at all scenarios, and explain the steps involved in direct design method of two-way slab design, and discuss the limitations or the factors that need to be checked before using the DDM, which is the direct design method. And then we'll solve one example problem for a two-way slab that is supported on beams using direct design method. So these are the expected learning outcomes. Right. So in the last part of the video or part of the module, we discussed that code coefficient method can be used only if they are resting on very stiff beams or walls. Okay. Now, when do you really say that the beams that are supporting this slab panel are quite stiff? Okay. So, for example, what we are seeing here is, let's say this is the panel that we are looking at. Okay, and this it's called as S1. Okay. Now this panel is supported on all the four sides by beams. Okay. Now if I calculate the relative stiffnesses of all the beams and the slabs which are part of this spanning, right? Then I get alpha parameter for called IB by IS. Okay. For example, let's say this beam when I take it is, it's going to look like a, if you look at it, this is going to look like an L beam to start with. Okay. So I calculate the stiffness of that. Then also I calculate the stiffness of the slab that is spanning. Okay. Now, for example, what would be the, for this beam, the yellow color beam that what we are looking at, what would be the slab dimension we need to consider? We need to consider from the edge of the panel to the middle of this. Okay. Because this is an edge panel. So like that, you consider different dimensions of the beam and slab, and you calculate your relative stiffness. Anyway, relative stiffness means EI, right, by L, right? So, but L for both beams are considered to be same. So L will get cancelled. Similarly, I is also same. Okay, both the slabs and beams are going to be cast with the same concrete strength. So the elastic modulus is expected to be same. So that is why it will get cancelled. So the relative stiffness will work out to be IB by S. And if the spans are different, then L2 by L1 will come. So this alpha B times L2 by L1 should be greater than or equal to 1. Then we can consider that particular beam to be rigid, quite rigid. Okay, so like that, all the four beams, what we do is we take the average value and we find out what are those average values of this stiffness parameter. If all of the average values are greater than 1, then we can say that the slab is supported on a very stiff beam. Then you can go ahead and use code coefficient method because it's relatively easy than direct design method. So again, why? If the beams are stiff, they are not going to undergo any deformation. So basically, we can isolate the slab panel and by assuming some boundary conditions, and we can derive the moment coefficient. So that is the idea behind code coefficient method. But if the beams are also deflecting, there is going to be an interaction between the slab and the beam. So we have to consider that interaction in analysis. Okay. So that's why the code coefficient method does not include this interaction effects. So that is the reason you have to make sure that the slab panels are resting on stiff beams or walls before using code coefficient method. And when you look at it, other extremes when there are no beams and when you have a flat slab, okay, so obviously IB value is going to be 0, right? So then the beam will carry no load and the full shear in the panel is transmitted by slab to the column in two-way action. So you can also have a flat slab or a flat plate without any beams, and the slab will transfer directly load to the column by two-way action. Okay, that is also possible. So that will happen when your alpha B parameter is going to be 0 because there is no beam, right? So this also we have to take it up. Right. So this is the way we categorize whether the supporting beams are flexible or stiff. If this value is less than 1, then we can tell that this beam is flexible. Right. So now that we understood what is a stiff beam and flexible beam, and when we have to use a code coefficient method, next we will discuss this another popular method, which is direct design method that can be used for slabs resting on beams, slabs resting directly on column, that is flat slabs. So every type of panel also we can use, but it has also own limitations. We'll discuss that. So what is a direct design method? So direct design method is an empirical method and it consists of steps to distribute moments to slab and beam section to satisfy safety requirements and most serviceability requirements simultaneously. So what does it mean? It is an empirical method where coefficients for moments are given for different locations of two-way slab. Okay, and how these coefficients were derived? They were derived based on single cycle moment distribution. Okay, we don't do the entire moment distribution because we have kept some boundaries, the limits within which even if you do single cycle moment distribution method, the results are going to be accurate. Only within that condition, we can use this direct design method, and it is an empirical method. And as it says, it consists of steps to distribute the moments to slabs and beams to satisfy safety and serviceability requirements. Now, let us see. Okay, as we have discussed, it involves a single cycle moment distribution and analysis of the structure based on the estimated flexural stiffness of the slabs and beams and columns. Here, we also need to include the transverse stiffnesses of the beams and slabs that are present. Because every joint, when you look at it, you're going to have a supporting beam slab that is spanning along the direction. In addition to that, you're also going to have beam in the perpendicular direction that is going to behave in torsion. So the torsional stiffness of this transverse beam also has to be included in stiffness calculations. Or in other words, this method is a simple method where we do only single cycle moment distribution and the code is directly giving you the values for moment coefficients, what can be used. Okay. But again, so because it's an approximated way of doing it, it's a simpler way of doing it, it has some limitations. So what are the limitations? They do not give satisfactory results for slabs with unsymmetrical dimensions and loading patterns. Okay, so if you are going to have a very unsymmetrical panel, and if your loading patterns are going to be, let's say, the live load to dead load ratio is going to be very high, then you have to consider pattern loading in the analysis. This direct design method does not consider all these effects, so it's a very simple method. Okay, let's look at the background. Okay, so what do we do in this direct design method? You have a two-way slab building with a two-way slab systems with different columns and beam layout. What we do is we divide the slabs into frames along east, west, and north, south directions along different column lines. So you divide them into different frames in the north south direction as well as along in the horizontal direction, that is your east west direction. So now what are the components that are going to be part of the frame, that we will talk about. Okay, and the next step is this method gives you steps to distribute the moments to slab and beam sections to satisfy safety and most serviceability requirements simultaneously, that we have already seen. And it also includes torsional stiffness of the slabs and beams transposed to the direction in which flexural moments are being determined. So which I will explain in the coming slides in a graphical form, as we have said. In the spanning direction where the slab is spanning, where we are calculating the moment, now I need to consider the stiffness of the beam that is running in the orthogonal direction that is going to contribute in torsional stiffness. So that we need to account in your calculations. And these moment coefficients, whatever that has been suggested by the direct design method, have been used satisfactorily for many years in regular slab design. However, also they give satisfactory results. Okay, they do not give satisfactory results when you have unsymmetrical dimensions and loading pattern. So what do you mean by unsymmetrical dimension? The successive span lengths should be within certain limit, and your live load to dead load ratio has to be within certain limit. So let's look at now what are the limitations of direct design method. Because when I derive these coefficients using single cycle moment distribution method, I have to set my boundary. Okay, the slab panels have to be within this, successive span lengths have to be within this, right? So I need to set the boundary to make sure that my approximation is valid, right? So what are the limitations or approximations we make? We This panel should have at least three continuous spans in each direction. So for example, when you look at this is not really a proper example. Anyway, so if you look at, let's say that we are doing this particular slab, okay, in this direction. So and then we divide them into two directions. Okay, so this is, let's say, this is your north south, and this is your east west. So if I divide the panel as frames, it should have at least three continuous spans. In this case, you have one and two. Similarly, for the east-west direction, you have one and two. So actually, if this is the slab panel we are designing, we cannot really use direct design method. You need to have at least three such spans. Then only the coefficients, whatever that is suggested, is actually valid. Next condition is each panel. Okay. For example, let's say this is one panel that we are taking. Okay. They have to be rectangular with the long to short span ratio not exceeding 2. Okay. So you can see that each panel has to be more or less rectangular. Little bit of offset is allowed, which we will discuss that. Offset for columns is allowed, which we'll discuss in the next point. But each panel should be more or less rectangular, and long to short span ratio cannot exceed more than 2. Okay, so it's going to have your in one direction, you're going to have more bending. Okay, let's say if your rectangular panel which has beams on all four sides, and if your longer to shorter dimensions of the panel is more than 2, then you know that you're getting into the territory of one-way bending, right? So then the coefficients, whatever that has been suggested for two-way action, will not be valid. Okay, the next question. The columns must not be offset by more than 10 percentage of the span. Okay, so for example, this is what we are looking at. In this case, if you look at it, let's say this is the span that we are considering. This is your L. Now, this column center line and this center line, if you look at it, the one column cannot be offset more than 10 percentage of the span along which you are calculating the moments. Okay, in this case, the span is L. So the column maximum it can have an offset of 10 percentage of the span. It cannot be more than that, because we know from architectural considerations it's always not possible to have columns along a straight line. So you will have a little bit of offset. So that the direct design method is accounting for it, but the offset should not be more than 10 percentage of the span length. Then the successive span lengths center to center of the supports in each direction must not differ by more than one third of the longer span. So let's say this is, let's say, L1, and this is, let's say, L2. Now let's say L2 is greater than L1. Now what we are saying is L2 cannot be greater than 1.3 times L1. That's what it is. Or it can differ means it cannot be greater than, also it should not be lesser than 1.3 L1 also. So these are the conditions we need to satisfy. Successive span lengths cannot be differing means either it can be higher or it can be lower also. So that is another condition, because within that range only the coefficients whatever that has been suggested is actually valid. Okay. Next question, next point is the factored live load must not exceed 3 times the factored dead load. Okay, if your live load is going to be very large than the dead load, once your dimensions are fixed, the dead loads are fixed, even superimposed dead loads to an extent, then they're not going to change much. But if your live loads are going to be much higher, then you know the pattern loading concept. So you have to position the live load at different locations to find out where will you produce the maximum moment envelope. So those kind of pattern loading is not considered in the direct design method coefficient derivations. So if your live load is getting to be more than 3 times the dead load, then you cannot really use direct design method. So cannot factor live load cannot be greater than, okay, this should be cannot be greater than 3 times the factor dead load, right? So these are the limitations. Now let us look at what are the steps involved. Okay, as we said, we are going to, let's say this is an example panel that we are considering. In the north, south, and east, west direction, you have 3 spans. Okay, and this is a fairly regular slab that we are looking at it. For this span along the east west direction, let's say this is L1. L1 is the center to center distance between the columns, and Ln is nothing but clear span between the column faces, right? Then what we do, first we discretize this panel as this is one frame and this is another frame and this is another frame and the last one is this. Okay, so you have this panel has been discretized into 1, 2, 3 and 4 frames along east-west direction, right? So that is the first step. We discretize a slab into frames in the east-west as well as in the north-south direction. So north-south also you will have in this case 4 different frames. That is the first step. Now you see here, always for the span we are considering, we denote the span as L1. In the direction of bending where we are calculating the bending moment, the span is always considered as L1. The perpendicular dimension of the frame is considered as L2. Okay, so this L2, this is a nomenclature. Usually, L1 is the span along which you are calculating the bending moments, and L2 is the perpendicular or orthogonal span. Okay, now what are the steps? For each, now that we have discretized the slab into frames, now let us look at what are the other steps involved. Once we discretize, we have to find the total factored static load. Now, what is total factored static load? So, if you go back to this panel, okay, whatever the load that is acting here, let's say I'm calculating for each span. So, this is the span. So, what would be the total load? Let's say the total load is WU, right? And total static, and it is acting over a distance of L2. So if let's say this is in kilonewton per meter square, when I multiply it to L2, which is a perpendicular dimension, I get it in kilonewton per meter. That total moment I have converted into, now this, when I multiply this, it becomes kilonewton per meter, right? Then moment is going to be Ln square by 8. So this is your total static moment. Like that, we have to calculate for each span. Instead of L1, here we use Ln, which is a clear span to calculate the moment. Okay, so this is the total static moment for each span. So that is the first step that we do. So as we said, W2 times L2 will give you kilonewton per meter times Ln square by 8 will give me the moment. Now we know that for an interior support, you're going to develop negative moment and positive moment. Okay, so here you can say this is, let's say, negative and this is positive. Okay, so this is support moment at this. So when I add this algebraic sum of ms plus mc, the moment at the center, it will work out to be equal to total static moment. Now, depending upon the boundary conditions, you can values can change. For example, let's say you have like this kind of support. Let's say it is subjected to W per meter. Now, what would be the bending moment diagram? Okay, you're going to have negative moment here and 0 moment here. So it's going to go like this and come like this. So what we are saying is this plus this, when I add it, let's say, so this whatever may be the boundary condition, when I add algebraic values of ms and moment at the center, or other words, what we do is we draw a straight line, and then when you add this at the center, you add the moments, it should work out to be equal to WL square by 8, which is your total static. That is a simply supported moment. Now, depending upon the boundary conditions, you can transfer some moment from midspan to support. Okay, on either side. Now, if you have fixed support, what you do? You develop negative moment at both supports, and then in that process, you reduce the positive moment, right? So in the same way is what we are having. Depending upon the boundary conditions, anyway, when you add the total static moment in a span should be WL square V. Now that some of them you will give it to support and some of them will reduce it in mid-span. So depending upon the boundary conditions. So first step is to calculate the total factored static moment, which is WU times L2 times Ln square by 8. Now, then once we've got for each span, we distribute this static moment into negative and positive regions, which is called as longitudinal distribution. Now, your discretization of a frame will have minimum 3 spans. So each span, you calculated your total static moment that you are distributing to how much it will go to the support moment and how much will go to the mid-span moment. That we need to do it for all the spans. So that is the next step, which is called longitudinal distribution. So the next step is called longitudinal distribution. How much it should go, that we will see. Once we get the longitudinal distribution, because the slab is also bending in the orthogonal direction, now the found out negative and positive factored moments has to be transferred to now column strip and middle strip. So that we will see in the schematics what is a column strip and middle strip. So this is called transverse distribution. So what is the first step? For each span we calculate total factored static moment. Then we calculate longitudinal distribution. Longitudinal distribution is how much moment should go to the support and how much moment should come to the mid span and all the spans. Then once we got this longitudinal distribution, now we are distributing in the transverse direction. So how much should go to the column strip and how much should go to the middle strip. This is called transverse distribution. These are the essential steps involved in direct design method. Okay. First we divide the panel into frames. Then we calculate total factored static moment for all the spans. Then we found out longitudinal distribution of the moments for all the spans. Then we distribute it in the transverse directions. Once you get your moment, the design process of calculating reinforcement is straightforward. That we know how to do that. Okay, so all in this method, all we are doing is actually doing structural analysis to find out the distribution of moments. We are not actually designing per se. This is a method to analyze this two-way slab in a simpler way and find out what would be the distribution of moments that I can be using for calculating the reinforcement. That's all we are doing. Right now, let's go ahead and look at it. So you see here, depending upon in the longitudinal direction, so this is what you said. So fixed beam, I can convert this into simply supported beam with n moments like support moments like this, right? So what we are saying is when you add this algebraic value of this plus this, right? This becomes your total factored static moment if the loads are factored, right? For a fixed beam, we can calculate what would be the positive moment WL 2 into ln square by 24. Negative moment is going to be WL2 times ln square by 12 or WL square by 12, right, for a beam that we have seen. Now, only thing is W into W here is in kilonewton per meter square. That is why we are multiplying by L2 to get kilonewton per meter and then ln square by 24 or 12 support. Now, when you add WL square, algebraic value of WU, let's say L square by 12 plus WU L square by 24, you will find that it works out to be WU L square by 8, which is your total factor static. Okay, if W is in kilonewton per meter. Okay, but usually for a slab, we define the load in kilonewton per meter square, and you have to multiply by L2 to get your uniformly distributed load of kilonewton per meter. So if you work it out, so this is total static moment is m naught. So if this is m naught, if it is taken, so then W U L square by this value, center moment we can write that as 0.35 times of your static moment, total factor static moment, and support moment can be written as 65% of your static, right? So this is it. For a typical interior beam, which is close to the fixed condition, your support moments are going to be 65% of your total factored static moment, because if you simplify this, 1 by 12 will be equal to 0.65 times of your m naught. Okay. So similarly, center span moment is going to be 35% of your total factor static moment. So now that we got this, let us see the second step is the longitudinal distribution of the moments in slabs. Okay. Now you have at the edge of the frame, you have an exterior span. At the interior locations, you have an interior span. Now we know that the interior span is going to approach fixed condition. However, the exterior span, it will also develop some level of fixity depending upon the beams that you are having in the transverse direction. And also you may have some walls that will be continuing along the facade of the building. So that will induce some fixity. So once we got your M naught, okay, for the exterior span, what the code is saying is the negative moment that I need to consider can be taken as 0.65 m naught by q. So for a fixed support, we know it is for interior support it is 0.65 m naught. But exterior in the exterior span, so this is exterior support. Okay, this is exterior support of exterior span. So this location is interior support of exterior span. So exterior span also having exterior support and interior support. Interior span is having two ends you have support which are inside, they are called as interior support, right? So now what are the distribution of the moments? If you see in the exterior support, the correct design method asks you to take 0.65 m naught by q. Now what is this q? Q is the relative stiffness parameter. So what is, again, m naught is, we have already seen, which is W times L2 times ln square by 8. Now what is this Q? To find out how much moment I need to design for this exterior support, I need to find out what is Q, which is a relative stiffness parameter. Q is defined as 1 plus 1 by alpha C, where alpha C is again the stiffnesses of summation of the flexural stiffnesses of columns at the exterior joint. Okay, how many columns that you have? Columns or walls. Okay, if you have a shear wall at the exterior also, we need to include that. Similarly, what is KSB? KSB is the flexural stiffness of the slab in the direction to the moments are calculated, that is along one. So in this direction, whatever the flexural stiffness slab that we are calculating for the slab, that I need to consider in your stiffness calculation. That we will see numerically how to calculate this value. So depending upon this fixity that you have, it may not be entirely fixed, but depending upon the elements how it is being connected, the code is saying that you calculate the stiffness parameter q and then you divide 0.65 m naught by that q to get what moment you need to consider for designing the exterior support at the negative moment location or a hogging moment location. Now what would happen to the positive moment? So the positive moment, if you look at it, we are taking 0.63 minus 0.28 by q into m naught. Okay. Similarly, for the exterior span, interior support location, we are taking moment of 0.75 minus 0.1 by q times m. Now you can ask me, how did we get all these values? So within the boundaries that we discussed, the limitation boundaries of the assumption that we made, people have done moment distribution analysis for different geometries, and then they have come up with these coefficients, which are reasonably close enough to the reality and produces conservative estimation of your moments. Okay, so this all these coefficients are coming from single cycle of moment distribution with some assumed boundary conditions. Okay. Now, for the interior support, it is very clear. It is going to be 0.65 m naught and positive moment is going to be 0.35 times m naught. Only the exterior span, you have to consider exterior span, exterior support, what is the moment, exterior span, mid span, what is the moment, positive moment, and then exterior span, interior support also you need to consider one moment. Okay. So these are the moments that we consider. Similarly, for interior span, it is very clear. At support, I am going to have 0.65 m naught, and at mid span, I am going to have 0.35 m naught. Now let us look at, so this is the second step. So okay, what are the three steps? For each span, we calculate total factor static moment. Then you look at the longitudinal distribution of moments, right? So now for this span also, if you have four spans, this will remain everything same. Everything will be considered as interior span. So your moment coefficients will be 0.65 m naught and 0.35 m naught here. So no change. Only at the exterior one, again it will change like this. Okay. So this is the second step. So step number 2, right? Now we get into step number 3, which is now that we got this longitudinal distribution. Now, why is it I need to do this longitudinal distribution? And you know that always a stiffer element will attract more load. Now, in the transverse direction, when you look at it, the slab that is close to the column line is stiffer. It's not going to rotate much, right? So, it is going to attract more moments in design compared to that of the regions which are away from the column line. So, that's what we do. The region that is very close to the column, we call this as column strip, like what we have seen here. It is a column strip. Now, this is your column strip from here to here. And then regions which are away from the column location, we call them as half middle strip on the left side and half middle strip on the right side. Okay. So each frame in the transverse direction, you will have a width that is close running along the column line as column strip. And on the right side of the column strip, on the left side of the column strip in a frame, you will have half middle strip, which we call that as a middle strip region. Now, why is that we need to divide like this? Because the regions along the column strip are stiffer. So that is going to attract more moment than what you're going to have in the middle strip region, right? So that's what we are doing. So if you go back in the previous case, we got all these moments, right? We got all these moments. Okay, this plus this, all these things are longitudinal distribution. Now, how much of this, let's say exterior support, exterior span moment, should go to column strip and middle strip? So that distribution is what we call that as transverse distribution. So now let's look at this. So in this case, now what was the M naught exterior that we got? M naught exterior, which we worked out to be 0.65 M naught by Q, right? So this is actually 0.65 M naught by Q, okay, which is this, right? So that's what we got, right? Similarly, we have different values for it. So if you look at it in the transverse distribution, what the code is saying is whatever that you get M naught exterior for the exterior span for exterior support, you put all of them in column strip only, because that is the region it's going to be very stiff. The moment you move away from column strip, the stiffness is going to drop significantly. It's not really going to take any load. So the code is saying that okay, you put all the support moment at the exterior location only in the column strip. So the columns is going to take 100% of this M naught exterior. So that is a assumption. That's a reasonably a good assumption. Then, when you come to the positive moment, M naught plus in the exterior span, what the code is saying is 60% of that will come to column strip. The remaining 40% will go to middle strip. So, remaining 40% means 20% will be put here and remaining 20% will be put here. So, of a total moment, 60% is accounted in or designed in column strip. The remaining 40% is put on the left side and right side of the column strip. That is half middle strip on the left side and half middle strip on the right side. Now let us look at what happens to the interior moment. Interior moment, when you look at it, interior column. Okay. So you see here 75% of the interior negative moment is accounted in column strip only. Only remaining 25% I am putting it as here 12.5 percentage, here 12.5 percentage, that works out to be 0.125 M naught interior. And why are we dividing by BHMS? What is BHMS is width of your half middle strip. So B stands for width and HMS stands for half middle strip. Similarly, this one is also same 0.125 M naught interior by BHMS, right? So in this way, depending upon wherever there are stiff regions which are along the column strip, the code is saying that, or the direct design method is saying that you put 60% in column strip. For example, mid span of exterior span, Whatever the moment longitudinally we got, 60% of them should go to column strip, only 20% on the left side and 20% on the right side. Similarly, the exterior location at exterior support, all the moment is taken only in column strip. So this region, it takes 100% of the total moment. Okay, nothing goes to here and here. So like that, the code is giving you, or the direct design method is giving you guidelines how we should distribute these moments. So this distribution is called as transverse distribution of moments in slabs. Okay, in the typical extent. Similarly, we do it for interior. Now, let's look at the clause 35.55 as per IS 456 2000. So, if you are doing a flat slab, the code is saying that negative moment at exterior, like what we have seen, if you have a column to wall width is ratios more than 0.75 times L2, then the exterior moment column strip I should take 100%. If your column width is less than 75% of your transverse width, then you design the exterior support column strip moment as BCS by L2 times M naught exterior. Then in the half the middle strip, now in the first case when your column to wall width is, see what we are saying is what is this column to middle width is? If you have a wall at the exterior location, and if your column is occupying, let's say, uh, almost 75% of your column or wall width, okay, both of the support, if the support is occupying more than 75% of the transverse width, right, then the code is saying that everything you put it in only in column strip. If it is less, then what is saying is that region is not going to be as stiff. So code is saying that you distribute the moment to column strip like BCS by L2 times M naught exterior, and the other region, whatever that remaining is there, okay, M naught exterior minus this BCS by L2 into M naught exterior, that 50% you go put on one half of half middle strip, another 50% you put in the another half of the middle strip. Okay, so that's what this is for, valid for flat slabs. And negative moment at interior support, I think it is very clear. We have already seen that whatever that we got support moment, okay, so actually, so this should be interior. Okay, so whatever that we got longitudinal distribution of M naught interior, M naught negative interior, 75% of them should go to column strip, and only 25% should go on either side. So that will work out to be 12.5, 12.5 on either side of the half the middle strip, not for the entire middle strip, half the middle strip on the left and half the middle strip on the right. Now for positive moment for all the spans, we are looking at 60% of the positive moment should go to column strip, and remaining 40% should go to entire middle strip. Now we are looking at half on the left and right side. Half middle strip will take 0.125 of the actually this should be actually, sorry, this should be 0.20. This should be 0.20 M naught plus, because the remaining is 40%. 20% will go to one half middle strip, another 20% will go to the another half middle strip. Okay, so this is what it is. So in summary, what are the steps? First we calculate total factored static moment, then we get the longitudinal distribution of moments, then we do the transverse distribution of moments. Now let's run through one example and see how to apply this method. Okay,